If you're rotating around the black hole, you are forced to co-rotate with it. Reality itself is rotating with the black hole. You cannot rotate against it. So a fun fact I like to tell everyone is if you're standing near a black hole and you stand there for one rotation, right, one rotation around the black hole, you will see the back of your own head. That's how relativity works. I am Dr. Ronald Gamble. I'm a theoretical astrophysicist and cosmic origins research scientist at NASA Goddard Space Flight Center and the University of Maryland College Park. The lecture today, or the talk today, is about the imaginative nature of black holes and space-time. What exactly is a black hole? Where do we find them? These are questions that we've always had for a number of years, if not over a century, right? Since the beginning of the advent of relativity in 1905, we've always asked the question, what if? And so it requires us to kind of be imaginative, as I said, about the nature of our reality, about cosmology, about weird things in space that we've seen over the past century, like blazars, black holes, even quasars, right? Even dark matter. But what exactly is a black hole? By definition, it's a region in space-time, right? And we're talking about up, down, left, right, X, Y, Z, T space-time, right? So we're really talking about our reality in 4 dimensions instead of 3. It's an area of space-time where the gravitational force is so strong and it's so compact that nothing can escape out of it, not even light, not even neutrinos or anything else like that. So if it's made of matter or if it has energy, it's really trapped inside of the black hole and nothing can escape out of it. So to kind of state about the history of where do we get black holes from, we actually have to go back to around the late 1700s. That's when the first idea, kind of presented by Reverend John Mitchell, presented the idea of some type of dark object in the universe, right? And back then, we didn't have an idea about black holes. We didn't even know what a dark star was. And that was kind of the original idea. But in 1783, right, that was the first instance of what we are trying to consider what a dark star was. And the idea is based off of, again, very simple Newton's law of gravity that was derived in the 1600s. So we're almost 100 years later, but now we're talking about things escaping gravity, light escaping gravity, and logically, what is that going to mean? Philosophically, what does that mean? Theoretically, what does it mean? So we're combining all these 3 areas together to now rethink our idea of our reality and what objects may be out there. So some black holes are formed by the collapse of stellar mass objects like stars. Our sun, for example, you're safe. It's not going to turn into a black hole anytime soon. It's going to turn into a red giant, as we theorize. But some stars do collapse, and in their dying ages, they turn and they transform into a black hole. You can think of it as a pseudo-force, if you will, right? Not quite a force like gravity or electromagnetism or the weak nuclear force or something like that, but you can think of it as a pseudo-force, something quasi that's happening, right, where if you're rotating around the black hole, you are forced to co-rotate with it. Reality itself is rotating with the black hole. You cannot rotate against it. So a fun fact I like to tell everyone is if you're standing near a black hole and you stand there for one rotation, right, one rotation around the black hole, you will see the back of your own head. That's how relativity works. I know it's a very weird idea, and you might think, okay, can we test this? Well, we can't, because we can't make laboratory black holes. That actually would be bad on Earth. But we can do the math, right? And we can see that where stars themselves, planets, galaxies, if you will, are being shredded around the black hole, right? We call those tidal disruption events, where they're being pulled around the black hole and the matter itself is being circulated around. And that's how we get something called an accretion disk. Now, if we zoom into the black hole, we'll find that in comparison to a non-rotating black hole, where you'll have a point singularity, right? So that very, very infinitely small point that we think is there, we have some singularity theorems and things like that. For a rotating black hole, it's actually a ring. So if you take a point, and you can do this on your sheet of paper, Draw a point on your paper. Keep the pen or pencil on the paper and then rotate the paper, not the pencil. And you'll find that you are actually creating a ring. That is what's inside a rotating black hole and a rotating charged black hole. So we have now very interesting ideas of, well, I no longer have a point singularity, but I have a ring. Well, what's inside the ring? Again, we don't know. And that's one of the things that we have to be careful of and be okay with in stating that, well, for a ring singularity, it's okay that we can say, I don't know, right? What's inside of a black hole? I get that question all the time. We don't know. And it's a fun question to say I don't know to, because it kind of ignites the curiosity of what's happening, around and inside the black hole. We're going to flash back to 1971, right?
Kim, we copied both solar wind and penetrometer drum in the ETB.
The Apollo 15 mission, this was a very classic, very well-known experiment. It was not done on Earth, it was done on the surface of the moon. David Scott and his colleagues kind of did the classic hammer and feather drop to see exactly, all right, if I drop something through space-time, if I drop something under the influence of gravity, if there's no gravity or very little, will they fall at the same rate?
Who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
Surprisingly, or to some scientists, unsurprisingly, they fell at the same rate, right? So this is, again, a very interesting, a very important experiment that was done simply to prove, yes, gravity is universal. It's not special on Earth, or it's not special inside the sun or on the moon. It's very universal, which means we can apply our laws of physics out in the cosmos, out to where the black holes are. And so now we're advancing to our modern day era in the 2000s and moving forward. 2015, we had the advent where LIGO, the Laser Interferometry Gravitational Observatory, detected our first kind of detection of gravitational radiation. These are gravitational waves, ripples through space-time. This is now measuring how space-time kind of vibrates, right? And if you can think of a prime example of you take two molecules together like a spring and you stretch them apart and you bring them back together, they will oscillate, if you will. They'll vibrate. That is what LIGO detected. Ripples, these are things that kind of go bump in the night in terms of gravity, if you will, right? One very important thing, though, is we found no deviations from the original 1950 general relativity. So again, Einstein, we like to call him a genius. I like to call him a creator. He was an artist, if you will, right? So in creating that art, it was a very, very foundational theory. And we can now measure things and introducing that happened early in this year and beyond. We're now measuring what's called the stochastic background gravitational radiation relics from the early universe, where supermassive black holes collided at the centers of galaxies and they smashed and they merged their event horizon together and to create very violent events. But those things created very high amplitude, right? Gravitational waves that kind of shook the universe, if you will. And these things are happening all across the universe. They're happening all across the cosmos. And we're measuring them today. We're even sending future satellites up to measure different types of gravitational waves. This is the LISA mission out of NASA, the Laser Interferometer Space Antenna, right? So again, this is LIGO in space, right? We're advancing, we're going into the realm of sci-fi in real life. So if you went back and you told Einstein, well, eventually your paper is going to be tested and we're going to do it in space, he'd probably look at you a little crazy, and then he would tell you, okay, cool, well, let me know how it goes.